Let's talk about the optical properties of materials. This is kind of a natural subject to discuss after we've discussed electricity and magnetism, because we can think about light as an oscillating EM field, in which we have one axis being our electric field, the other the magnetic field. This is the direction of propagation. Then you'll have an electric field in this direction. And then perpendicular to the electric field, there will be a magnetic field that is oscillating alongside it. The electrical and magnetic components are at right angles to each other. When we discuss the behavior, the properties of EM radiation, we discuss it in terms of the energy, the frequency, nu, and the wavelength. Lambda. And there's relationships between these. Most notably, the frequency and the wavelength are related by the speed of light in vacuum. So, lambda nu. So this has units of meters. Frequency is inverse seconds, so this is meters per second, and it's the speed of light in vacuum. Which we'll discuss shortly is going to be different than the speed of light of an EM wave passing through a material. The energy is written in terms either of the frequency or the wavelength. In which this h is the Planck constant, and has the value 6.63 times 10 to the minus 34 joules second. And it has joules second because this is 1/2. And this is energy. So this Planck's constant is actually something that's very much tied into our understanding of quantization. And when quantum mechanics was first being discovered in the early 1900s, this Planck's constant showed up repeatedly as properties became quantized. The speed of light in vacuum can also be related to the behavior of electrical and magnetic fields in vacuum. In particular, it is related to the permittivity in vacuum, or of vacuum, and the permeability. we talk about the properties of light, we talk about the intensity, and put a knot there to be the incident intensity. Of light coming in. And then we can talk about the intensity of the light that is transmitted, and that will be naturally less than the incident. Part of the loss going from incident to transmitted is due to reflection, and part of it has to do with the scattering, and more importantly, the absorption processes in the material. So we can say that the total incident beam either is transmitted or reflected or absorbed. If we take this and we divide it through by the incident intensity, that will normalize this relationship and give us 1 is equal to T plus R plus A, where that is the transmittance, that is the reflectance, and that is the absorbance. Basically, it's giving us the fraction of the incoming light that goes through one of these 4 processes. Now, I talked here about scattering and absorption. I think it's worth commenting that we're interested in talking about absorption, not necessarily scatter. Scatter, you can think of actually as more of a multiple reflections, right? If you imagine versus absorption. If you think about, say, a sheet of glass or a sample of some sort, you're going to have some incoming and some transmitted intensity. And you think, well, okay, that means that it's either going to be reflected or absorbed. It can also undergo scattering. So imagine this is, say, just plain window glass. One other thing you could do is you could take window glass and you could grind it up into a fine powder and then press it back together and heat it up slightly so that those particles reattach. They basically will kind of sort of melt together slightly. This is called sintering. And if you do that, what the final product will not be optically transparent, but instead it's going to have kind of a white, typically white, a surface. And what's going to happen is if you have some incident light, then you'll have multiple scattering and you're actually going to have a significant loss. And this is a different process. So when we are discussing absorption here, we're primarily going to be discussing absorption in which the properties are not due to microstructural features, but are instead due to intrinsic optical behavior. So let's begin by talking about a class of material which is, in some regards, kind of the simplest to discuss, and in others, not so much. Metals. Metals are opaque. And the reason that they're opaque is that we get a transmittance of 0, reflectance, which is relatively high, anywhere between 90 to 95%, which gives us an absorption that ranges then between 10 and 5%. Metals have free electrons, and those free electrons will move through the system, and when an alternating electric field approaches a metal, what's going to happen are the electrons will rearrange themselves on the surface to counter the incoming field. And this is just on the surface. So call this surface electrons move to oppose the field. This can be called a skin effect. And as a result, there will be no electrical field inside true metals. The skin is typically around 1 micron. That's 1 times 10 to the minus 6 meters. And to a certain extent, this means that the optical properties of metals are fairly set. It's worth noting, though, that the behavior of the skin effect does depend on the particular metal you're looking at. Right? If you ask yourself, what gives metals their color? This color, for example, why is gold, silver, lead, gray? This has to do with the electrons on the surface. So these free electrons, they can move around kind of collectively, and that is called a plasmon. Collective motion. And just as any kind of wave problem you're looking at, you're having electrons that are sloshing around and whatnot, the boundaries are actually quite important. And at the boundaries, we're going to have resonant frequencies. And these resonant electron waves on the surface give color. And what's neat about this is that you can use this as a method to change the properties. And kind of the best example of that is what's called Black Hills gold. And Black Hills gold was really first, came into popularity around the 1870s. This is gold, but it also is not just gold color, but you can get it in green, you can get it in pink. So that rose gold, that is a type of Black Hills gold. You can get different variations of silver and yellow. And this has to do with having a gold that is then doped with other elements, such as copper, platinum, silver. And essentially we're changing the concentration of electrons, and that when you solve the wave equation for electrons in this material will change the resonance states, therefore change the color. Now moving to non-metals, which are a little more interesting. In the case of non-metals, the electric field will penetrate into the material, and the electric field interacts with the electrons that are around the atoms. So you can imagine you've got some oscillating electric field, then the atoms, which have a positive center and have some electrons around them. These electrons will become mobile, and you'll get an oscillation of these. And when they oscillate, then they will further emit an electric field, and they'll pass from one to the next until they get to the other edge, and they will give off a electric field. So you have transmission through nonmetals via the interaction of the electric field that's oscillating with the electrons around the atoms and the bonds. As a result of this, you can certainly imagine that a wave traveling in vacuum or air will have a different velocity than the electrons that are in the material. And the velocity, of course, is going to be less than the velocity of light in a vacuum, and they can be related via what we call the index of refraction. So C is equal to N V, where N is the index of refraction. And vary from material to material. This change in velocity also will correspond to light being refracted. If you imagine us having, say, vacuum, and here, say, glass. As light comes in, instead of just coming out the other side, it will be refracted to change direction and then come out. And this effect called refraction is something that you've probably seen before. This is why if you have a glass of water and you have a drinking straw in it, the drinking straw will look slightly broken. If you've ever tried to reach into a stream or a pool of water and grab something, you'll see that just because something looks directly in front of you, it's actually shifted a little bit, and that's because the image of the material has been shifted. The degree of refraction has to do with the difference in the index of refraction between the different materials. So let's say I have some material, say 1, and material 2. Here's the interface between them, and I'm going to draw the normal to the interface. If I have an incident light source, that theta 1, the angle of incidence, and then comes off in that direction, call that theta 2. The angles here are related by what's called Snell's law, which is that N1 over N2, for N1 is for material 1, N2 is for material 2, is equal to sine theta 1 over sine theta 2. And it's also worth pointing out that this index of refraction does depend on the frequency. So here, for example, if this is some monochromatic light, something, whatever light from a laser or what have you, it's going to have a very well-defined angle. If instead it was white light, then depending on what the color of a particular photon is, you're going to get a different bending. And that's why if you have, say, a prism, some type of glass you can send light in, and what's going to come out is going to be a rainbow, because they bent or were refracted to different angles as they passed through this glass prism. It should also be pointed out that this velocity is going to depend strongly on the polarizability of the material. If you want to imagine, say, the difference between, say, the positive and the negative centers of charge as being attached by some spring, that essentially is telling us about the polarizability. It's telling us about how hard is it for us to separate these. What is the force required? A material that has a relatively high polarizability, meaning that it's relatively easy to separate the positive and negative charge, the velocity will be lower. In contrast, something which has a lower polarizability, it will have a faster velocity. What you can picture is, if you want to picture, say, some system with balls with springs between them, and some lattice of that, and you imagine trying to put a wave through that. If you have relatively stiff springs, you're going to have relatively rapid transmission. If you have sloppy springs that are weak, meaning it's relatively easy to separate them, relatively easy to pull these masses apart, you can imagine that passing a wave, whether it's an elastic wave or electric field, are going to be relatively more difficult. And as you may have imagined, the velocity is also dependent on the behavior of the material with electric and magnetic fields, meaning that the velocity can also be related to the permittivity and the permeability of the particular material, to the negative 1/2, which means that if we want to talk about the index of refraction in terms of C and V, it's going to be equal to the square root of epsilon mu by epsilon naught mu naught which means that the index of refraction is equal to the relative permittivity and the relative permeability. And the typical range for n is going to be between, say, 1.4, 1.8 for ceramics. Certainly, you can make kind of advanced engineering materials which have specialized properties, possibly larger. 1.35, 1.6 for polymers. So this brings us to reflection and or the reflectance. And this can be written also in terms of the difference in the index of refraction. So again, N1, I0, IR, N2, and this is going to be equal to N2 minus N1 over N2 plus N1 quantity squared.